This lecture is rather formal because I'm going to introduce the notion of tensors, explain the geometric meaning of Christoffel symbols which have appeared at the end of the previous lecture, and I'm going to explain what is the difference between flat space and curved space, how to distinguish what is just flat space in curvilinear coordinates in comparison with curved space. And so I assume that those who listen to these lectures are familiar with tensors in flat space time, and so my introduction will not be very basic, so I will assume this knowledge. So let me just remind you that coordinates, if I have a coordinate transformation, x mu going to x bar mu, which is a function of x, original x, then the coordinates themselves transform tautologically. Tautologically means that dx mu is equal to dx mu over dx bar nu, dx bar nu. Well, this is a tautological transformation because if I divide both sides by dx bar nu, I just obtain equality between the same thing. So, but it is important to bear in mind that the vector is referred to as contravariant if it is transformed in the same fashion. So the vector is contravariant, so it carries upper index if it transforms as coordinates do. So like this. So such a vector is referred to as a contravariant. Covariant vector is transformed differently. It transforms as one form. So it carries lower index, and transforms according to this rule. So this is a function of x. This is a bar mu function of x bar already, multiplied by a dx bar mu. And as follows from this relation, we obtain that a mu of x is just dx bar nu divided by dx mu a nu bar of x bar. So this kind of vectors are referred to as contravariant, this as covariant. So now if I have a metric tensor, it means that I defined line element in the space-time like this, mu nu. And since the last lecture we are familiar with the fact that metric tensor can be in principle arbitrary function of x. So if we have a metric tensor and we have its inverse tensor with upper indices, where this is a Kronecker symbol, which means that it is 1 if mu equals to alpha and 0 otherwise. So if we have two tensors, metric tensor and inverse metric tensor, to every contravariant vector, with the use of the metric tensor, we can define corresponding covariant vector. And vice versa. If I have covariant, but multiplying by this, I obtain contravariant vector. It's important to understand that due to this relation, the components of this guy coincide with the components of this guy. So this operation is reversible. Now, what is a tensor? What is a tensor? Tensor is the following quantity, n tensor. Is the following quantity. It carries n indices, some of which are upper case, and the others are lower case. the order of indices is important, but in this formula, to simplify it, I just ignore this fact. I will stress it later, why the order is important. So, but it's important that L plus K here in this formula is just equal to n. So the total number of indices is n. So the such a tensor is a concrete quantity which transforms appropriately with respect to the coordinate transformation, which means that these indices, uppercase indices, transform according to this rule, nu1 divided by dx bar alpha 1 dx nu L divided by dx bar alpha L, and vice versa for these ones. So it's dx bar beta 1 dx mu 1 dx beta k bar divided by dx mu k multiplied by, so this is a function of x, this tensor is a function of x, multiplied by t bar of correspondingly beta 1 beta k, and here alpha 1 alpha L as a function of x bar. So if there is a quantity which under coordinate transformations transform like this, we call this as n tensor. So vector is just a variant of n tensor with only one index. So it's a one tensor. The simplest tensor is a scalar, a quantity which doesn't have any index and which transforms trivially under the coordinate transformation. Trivially in the sense that it just transforms from being originally it was a function of x and became some new function of x bar. So this is a rule for the transformation of a scalar. Vectors are like this. Now, why does one need tensors? Why does one need tensors? As I explained in the first lecture, we need to write laws of nature. I mean, dynamical equations of motion describing motion of particles, or dynamical equation of motion describing space-time changes of the fields. We have to write them in a covariant fashion, in the way that the equations of motion do not depend on coordinate system. They change. So in the bar system, they are expressed through the bar quantities, bar tensors, bar coordinates. In the original, through unbarred quantities. So for defining this kind of laws of nature, we need tensors, because tensors are quantities which are transformed appropriately with respect to the coordinate transformations.